Hello, Padres. We are going to talk about temperature and heat for this last section of our energy notes. So here we go. We're going to start with the differences between temperature and heat. Are they same? Are they different? Temperature is signified by a capital T. It is the average kinetic energy of the molecules in a substance. So the molecules in any substance are vibrating, and if they have if they have a higher temperature, those molecules will be vibrating faster. And I like to think of temperature as measuring the hotness of an object, how hot or cold something is. And we measure it in 3 scales: Fahrenheit, Celsius, and Kelvin. We'll be using Celsius in this class. Absolute zero is the temperature where the kinetic energy is 0. It is a theoretical temperature. We can get very, very close to absolute zero, but we can't actually get to it. You can think of there being asymptote right there at absolute zero. And some common temperatures: in Fahrenheit, water freezes at 32, boils at 212. Celsius, it's 0 and 100, and Kelvin, 273 and 373. As you can see, most of the world does use Celsius. There are about 6 or 7 countries that use Fahrenheit, the main one, of course, being the United States. Thermal expansion. When things get hot, they get bigger. And this happens because the hotter they are, the more kinetic energy there is. That means the molecules are vibrating faster. And if they're vibrating faster, they're hitting the walls with more energy, and that pushes the walls out. And so this is the reason why bridges have these little metal grates in them. You can see they're kind of like a zipper almost, and it allows the bridge to expand and contract without the bridge breaking. Railroad tracks have the same thing. If they don't, then on a hot day when the tracks expand and get longer, if there's no way for them to expand into, the tracks can bend and buckle like this and cause the train to derail. Heat has the symbol Q, and heat is the flow of energy from one object or substance to another because of a temperature difference. So heat is the flow of energy. So if you have some lava and you stick a thermometer in the lava and the lava is 1,000 degrees, that is the temperature of the lava. If you stick your hands out and you feel the heat coming off the lava, you're feeling the energy. So one is the energy coming from the object to you, that's the heat flowing, and then how hot it actually is, that's measuring the temperature. The unit of heat is joules because this is an energy, and heat always flows from hot to cold in nature. Thermal equilibrium is when no heat flows, and heat doesn't flow when the two objects are the same temperature. So here we have block A and block B. Block A is hot, block B is cold, and when they're in contact, they're in the middle image, heat flows from the hot to the cold one until eventually the hot one is going to cool down because it's losing energy, and the blue one, object B, is going to warm up because it is gaining energy, and they're going to eventually meet at the same temperature. Here's a video that kind of talks about heat and temperature, what we were just talking about. I'm not going to play the video, but you can go into the notes, which are on Google Classroom, and you can watch the video yourself. All right, so a few questions and answers. Can an object have heat? The answer is no. Objects have temperature. Heat is the energy that flows off of hot objects. Question 2, when heat flows away from an object, what happens to its temperature? As heat flows away, the object is losing energy. So as it loses energy, the temperature is going to decrease. When you open the fridge, does energy flow into or out of the fridge? The energy flows into the fridge from hot to cold. So when my mom would always say, "Close the refrigerator door, you're letting the cold air out," she was wrong. You're not letting the cold air out, you're letting the hot air in. And finally, you pour some cold milk into hot coffee. What happens to the temperature of the milk and the coffee? Well, the milk is going to get warmer and the coffee is going to get colder until they reach the same temperature. All right, second part of the notes. Has this ever happened to you where you microwave a bowl and the bowl is really hot when you pull it out of the microwave and then you take a bite of your food and the food is cold? This has to do with specific heat. It's the same reason why you would grab the wooden spoon out of this boiling pot of soup, it looks like. You don't want to touch the metal spoon because it's going to be too hot because they have different specific heats. So what is specific heat? Why is the food colder than the bowl? Why is the wooden spoon cooler than the metal spoon? It's because of specific heat. So specific heat is the amount of heat needed to raise the temperature by 1 degree Celsius. So for the microwave with the bowl and the food, both the bowl and the food are receiving equal amounts of heat from the microwave. The bowl takes the heat and the temperature goes up right away because of the specific heat. The food takes the same heat and it absorbs it and it doesn't raise its temperature. So because the properties of the materials, because they have different specific heats, the temperatures will either increase or decrease faster or slower depending on their specific heat. So I kind of liken this to thermal inertia. So remember, inertia measures how stubborn an object is or how much it wants to resist change. So things with a lot of inertia are like a train. They're very hard to get started and they're very hard to stop. That would be like the food. It's very hard to get warm and it's very hard to cool off. And something with low inertia would be like a skateboard. Easy to start, easy to stop moving. This would be something like the metal spoon. It's very easy to get the metal spoon hot and it's also very easy to cool it off. The units are joules per gram degree Celsius. And high specific heat means hard to heat up, hard to cool down. It has a high thermal inertia. Things like water and wood have high specific heats. Low specific heats are the opposite. They're easy to heat up, easy to cool down. These are things like metals or sand. If you walk on the beach on a hot day, the sand is hot. And if you walk on the beach at night, oftentimes the sand is very cold or cool. So the sand heats up fast and it also cools down fast. Specific heats are constants. And so whenever we do any problem, I'll always give you, if not this table, a table, and the table will have different specific heats on it that you can use for reference. So it's a number, a value that we can look up. And the last few slides are math. So we're going to be looking at we can go over this one real quick. The math is Q equals mc delta T. Q is the heat. C is the specific heat that we read from a table. M is the mass, and delta T is a change in temperature. And most often we're going to be writing it this way, where we have the change in temperature expressed as the final temperature minus the initial temperature. So here's an example. How much heat is needed to raise 20 grams of water from 15 degrees Celsius to 20 degrees Celsius? So we're going to write down what we know. The Q is our question mark. M is 20 grams. We're trying to find, we're trying to find the heat, but our change in temperature would be 20 minus 15, final minus initial, so it's 5 degrees. And the specific heat, the 4.18, is what we would look at on the table. Q equals mc delta T is our equation. We plug those numbers in, and we get 418 joules. All right, the next is thermal equilibrium. Thermal equilibrium, we are measuring the heat lost is the same as the heat gained. So mathematically, we can write that as minus Q equals positive Q. So minus Q, the hot one is losing heat, so that's negative. And so we can use this equation where we're basically saying, it's basically saying the same thing as the line above it. And we have some examples. We'll do those in another video tutorial. We'll go over some mathematic examples where I have the pen, I'll write it out. So thank you. This is the end of the heat portion of our energy unit. Thanks for joining in. I will see you guys next time.